Hi everyone. Just wanted to let everyone here in and it'll just be, we'll wait another minute for everyone to show up. And now that we're at 2 minutes over, I'll just get started with the housekeeping. Thank you everyone for joining today. We're really looking forward to this presentation. Um, This will be recorded and distributed by end of the week, the slides and the recording itself. And you can find everything that we've done in the past couple of years on our website on the archive tab. If you have any questions, please feel free to raise your hand, drop your question in the chat, or use the questions function. We can get to those at the end, or if our presenter prefers, she can answer as we go along. But if you also want to come off mute, just please raise your hand and I can take you off of mute and you can ask your question that way as well. And with that, I'll hand it over to Malin and we will get started.
All right, thanks, Kate. So yeah, my name is Madeline Talibi. I'm with ICF. I'm one of the energy engineers on the team, and I support the Gas Emerging Technologies program that's in partnership and collaboration with SoCalGas. And today I'm going to be talking about one of the projects we have going on. We have several with looking at GHP units or gas absorption heat pumps. This is going to be focusing, we've been coining it number 2. It is the ANISI model, and we'll look at a full comprehensive performance mapping that we did in collaboration with GTI Energy. So I have myself listed here, the 2 project leads from GTI, Lee and Ari, and then just a brief agenda about what I'll be discussing today, so why we're interested in this, some of the overarching lab study objectives, our test plan, and then kind of the main bulk, I would say, of this project. So looking at steady state and load-based testing, and then taking those, leveraging that data, taking that and looking at, okay, how can we develop some Energy Plus modeling correlations and then future recommendations going forward. And then just want to acknowledge all the project collaborators from ICF and then from GTA Energy as well. So gas absorption heat pumps, as I mentioned, we were looking at the ANISI unit for this study, so the number 2 study. And then why we're interested on GHP units specifically in California. So if we look at water heating, it is going to be the largest non-industrial end use of natural gas, specifically in California. And so I have this graph here, which shows some natural gas consumption according to end use. And that's according to industrial, commercial, residential. So looking at why are we interested in GHP units specifically in this case, going to be the commercial sector. So it's not the most impactful of this, but the scale is quite large nonetheless. And according to these several California bills and legislation, if you've seen some of the GHP conversations or talks that I've given in the past, this is kind of my boilerplate slide that kind of, so you've probably seen this before, but overall, according to these California bills and legislation, there is a push to get energy efficiency technology and measures into the multifamily sector, into multifamily housing. And so we're kind of coupled with the water heating being a very impactful sector where we can, or I guess end use where we can make a significant difference. So kind of looking at pushing towards the multifamily sector. And I've listed these here. I won't go through the nitty-gritty details, but if you're interested, and diving into those California bills and legislation, please feel free to do so. And then some overall objectives. So we want to, again, improve the low uptake at the sector level, so that being the multifamily, improve low uptake at the technology level, so where there is kind of a gap for GHP usage, look at technology performance, so that being equipment commissioning, steady state evaluation, part load evaluation, develop those performance mapping curves that we can use in Energy Plus and that GHP module that's already existing. And then again, this is the #2 study that's in kind of correlation to the #1 study, which was for the Rober GHP-A unit. And I have that study listed here according to the name that we've kind of given it for this Gas Emerging Technologies program. So if you're interested in reading that comprehensive report, I presented on that one as well for this public dissemination forum. So at the end, I'll kind of look at comparing how does the ANICI relate to the Rober unit. And so before I get into some of the testing, just want to give an overview on some of the equipment commissioning and the test plan. So this is the unit that we are testing in this case. So you'll see it in my slides, just kind of called ANICI GHP 80K system. So overall, for any rates that I have listed here, so the flow rate, the firing rate, the heating output, we're going to look at a ±2% tolerance. And then for the outside, any of the temperatures, so that being outside air, return, supply, we're looking at ±1 degree Fahrenheit. And according to the commissioning, everything was in positive agreement with those tolerances that were set beforehand. And then for that steady state testing, this is kind of a high-end or high-level overview. So looking at the firing rate, so kind of breaking it up into 3 different points. So that being at a 25%, or we're calling this the minimum firing rate that you would ostensibly see the ANICI unit at. So that's at about 14 kBtu per hour. Right at the midway point, so 50% of its firing rate capacity, so 28, and then 94, so not quite at 100, but just 94 is the max that the ANICI unit is able to fire at, given its modulating controls that are integrated into the system. And I'll probably touch on that a little bit more later on into the presentation. And then looking at the outside air temperature, range of 0 to 110 degrees Fahrenheit, so 9 points within that range. The return temperature, 95 to 140, so 5 points within that range. And then the propylene glycol volume percentage was kept constant at 35. And the steady state testing was mostly used in order to essentially set the baseline for what we can use for the part load testing. And so for that part load testing, it was set up in 3 different kind of chunks or different types of testing. So first being looking at standby losses. So looking at measuring the tank losses under a no draw condition. So kind of modulating the system as it is essentially configured and kind of leveraging some of those modulating capabilities of the system. So again, the first one was a standby testing. Then looking at a low draw testing, so essentially waiting for the unit to cycle to its lowest firing rate and then completely cycling off. So I have those different testing points that were looked at for this type of testing. And then lastly, this was a draw pattern testing. So looking at actual field data of a multifamily building, the different load profile, essentially, the variations that coincide with that, and then looking at these different testing ranges that I have listed here. And so now I'll get into an overview on the results. So this is for the steady state testing. So first and foremost, looking at the firing rate. So these gray, orange, blue are going to correlate to the maximum firing at 94%, the median, we can call it at 50%, and then the lowest at 25%. So as you can imagine, the gray curve is most likely always going to be at the top just because it's at its highest firing rate. So you can see that the firing rate is going to decrease with an increasing outdoor air temperature. And this is a reduction of about 11 to 18% from 0 to 60 degrees Fahrenheit. And then looking at the power input. So this is essentially trying to understand, is there any sort of large power discrepancy that we see when we're looking at, okay, is there going to be a large fluctuation? Is there going to be a large load demand, given that this is mainly a GHP unit, but there are some electrical demands corresponding to this unit itself. So we see that it's minimal in this case. It's almost negligible. So it's nearly constant And then a lot of the electrical power is going to be coming from the solution pump, the air coil fan, and any other the controls. And then looking at the output, the heating output, so we see the heating output is going to peak at a full firing rate. Essentially, we're seeing it here peak at that full firing rate, and it's going to happen between 40 degrees Fahrenheit to 60 degrees Fahrenheit. And this is the essentially the normalizing unit that we're using for this x-axis. So the return temperature minus the outdoor air temperature. It's going to be nearly constant at 50% and 25% firing. We see that there's very minimal, if not negligible, variation. So then if we see the heating output is going to, of course, vary depending on the firing rate. So if we normalize that to the corresponding input ratio, we can essentially see how much of an overlap there's going to be to understand, okay, what's the overall difference going to be between the 25% firing, the 50% firing, and that maximum 94% firing. So at the full and mid firing rate, they're closely correlated. The low firing rate is going to have more variation, and it's going to be due to the occasional cycling just at the ANSI GHP 80K boundary limits. So again, according to those controls and how they're set, you want to be wary, again, depending on the application, of hovering too low, just because you could essentially hurt your COP or your overall efficiency of the unit if you're hovering at that too low of a firing rate. And then looking at a comparison, so the COP gas only, and then on the right-hand side, the COP gas plus electric, and that kind of touches back on that power input curve I mentioned at the beginning where we saw a near constant. So looking at this from taking a step back, you virtually see no difference between the COP gas only and the COP gas plus electric, but nonetheless wanted to show this. We would expect this, again, according to that power input curve. So looking at the COP gas only curve, so we see the COP remained above 1 over the entire range, and there's more thermal output than energy input. That's what that overall signifies when we see a COP above 1. And then the COP is about 1.2 to 1.4 for return temperature, outdoor air temperature, normalizing factor of 40 to 80 degrees Fahrenheit. So those are typical common operating conditions. So that was a positive finding. In this case, we want to optimize the COP as much as possible. That's going to reflect how efficient our unit is and how optimally it's been configured. And so when we see comparison purposes, we see the COP gas plus electric. So we see that the COP does drop about 5% at that minimum firing rate. And it was minimal, about 3 to 5% difference if we're looking at the COP gas and then the COP gas plus electric. And then again, this is attributed to that low electrical usage that's required for the unit. So now that we've essentially established our baseline, we can get into looking at some of the load-based or the transient data. So before I get into that, I just want to mention something that GTI had found when they were looking at configuring this. So they did adjust this slightly. So this is a steady state testing that was performed on this unit and with a controlled return temperature, as I was mentioned, according to that the test plan that was outlined at the beginning of this presentation. So for that standby, low draw, draw pattern, those 3 different part load test parameters that were set, those testing was performed on a system with an indirect storage tank. So the storage tank, about 119 gallons and with an internal heat exchanger. And so looking at those load-based testing, so in the event of looking at the draw pattern, so there were some issues with the unit itself. There was some contamination of the refrigerant. And so you can see the difference that we have outlined here with the draw pattern on the original unit. And that was the original unit that it came to find out that there was some contamination. It happened in the expansion valve of the system. And so tried flushing it out. That didn't correct for the issue that was being seen. So a full replacement unit was set, and you can see the difference in the performance where it was performing back up to the expected conditions. And then looking at the steady state modulating firing rate, so looking at this as a function of the part load ratio. So the part load ratio or part load unit performance of 25 to 100% is ultimately based on the steady state testing at reduced firing rate. And then the testing of the previous unit, the non-modulating, so the previous unit being the Rober. So I mentioned I might touch on this later on in the presentation. So the biggest difference between the ANSI and the Rober, which was the GHP #1 testing, and we kind of had to navigate with the rover, is that there's no modulating capabilities on the rover. It's either on or it's off. It's either firing or it's not. So with the NICI unit, that's why we kind of had to slightly shift how we were going to test this to try to draw a comparison. It's hard to draw a comparison when the controls of the unit are not innately the same. And so came up with this draw pattern testing, the low standby testing, and so forth. And so looking at testing of the previous unit, and again, this is based on the cycling on and off. And so we see the difference between the part load, which we would expect at 100%. We're seeing at full fire, we're achieving overall gas coefficient performance ratio of 1, which we would expect in this case. So that was, again, a positive finding. And I'll show later on a direct comparison between what the rover unit looked like and then what the NEC unit looked like. So you can see kind of, okay, what were the differences between the two? And then just wanted to touch on this. So this was looking at the NEC unit with tank system performance. And so testing using the draw pattern at low, medium, and high draws, again, was performed. There is a COP benefit, along with there's going to be interconnection losses and tank losses. So interconnection meaning between the units themselves, there might be some losses that happen. And then, of course, any tank losses are to be expected in this case. So this was looking at one data point. This was just to kind of exemplify this type of behavior, what we might expect. So if the COP is, let's say, at about 1.35, according to this graph, the interconnection losses, that might fluctuate. It depends on how it's configured. Of course, there's a lot of studies happening right now in terms of trying to make somewhat of a blanketed tool that looks at, okay, how do you install these GAHPs to get the most efficient configuration. So that might fluctuate, but the tank losses are kind of innate to the system. So if we look at, okay, what are the overall COP going to be with this indirect storage tank linked to this GHP unit, with a 1.35 minus the 8% losses, you could still expect about 1.27 COP, which is, again, is to be expected based on some of the part load data and is a very positive finding in this case. And then lastly, looking at the load-based performance mapping. So looking at 50% firing rate, you see a minimal performance drop-off. So 50% being these yellow dots right here, 25% firing rate. The COP does drop by about 10% lower than the steady state. And then at very low usage, so that being the standby conditions, your COP is at about 0.8. So you could see the variation in the part load, excuse me, as the part load fluctuates, you can see the variation in those different data points that were tested. And then briefly touching on some Energy Plus modeling. So overall objective, what we're looking to do here is forecast energy consumption, utility bills, and greenhouse gas emissions. A targeted audience, it really could be anybody, but just to hone in on a specific audience, it could be California policymakers, program designers, software developers, and of course the manufacturers. And so looking at developing these modeling parameters, so looking at the modeling parameters themselves, they could be predicted within a plus minus 5% at full load, plus minus 10% at those lower part load ratios. And then I have these key parameters that have been somewhat outlined just at a high level. I won't go into the nitty-gritty details. I think the report itself is very comprehensive in that sense. If you want to kind of follow this overall calculation approach, I think it does a good job. And these are kind of at a high level, some of the main heating capacity gas use that were being targeted when trying to predict the overall COP of the system, again, using some performance mapping correlations. And so looking at those, so the thermal output, the thermal input, the COP, so as I mentioned, plus minus 5% at full load, that's a very positive finding in this case, plus minus 10% at the lower part load ratio, given some of the modulating functions that are built into the NEC, along with any cycling errors that might have happened. This is probably to be expected as well. Just there's a lot of unknown error that might happen or correlate with that. And then finally, looking at the Rober GHP-A unit versus the NEC unit. So overall, there was similar performance that resulted between the two units and over the operating conditions that were tested for all of these. So if we look at the Anisi GHP 80K unit, it was about 77 to 10% higher over the tested range. It was similar, but ultimately the Anisi did show a higher COP than the Rover, and I do want to attribute, I believe it is attributed to the modulating controls that are built into the Anisi. You don't have as high of a risk of reaching any short cycling or deficiency in the operation of the unit. So this was just looking at a steady state comparison. So looking at, okay, let's look at a 80-degree Fahrenheit. Again, this is probably within 40 to 80 degrees Fahrenheit is where you would see this GHP unit operating. So looking at the Rover, we're at about 1 to 1.1, and then the Anisi unit is slightly higher at about 1.2 across the different modulations of the different firing rates that were tested. And then looking at that part load performance comparison, so the differences are going to be independent of the flow rate and the firing rate. We see in this case for the Rover unit, we're at about 0.82, I would predict. And then similarly, we're about, let's say 0.82, 0.8 in this case. So again, minimal difference between the two units for that load-based testing, which would most likely be the actual field data that you would never have something operating in under steady state. And let's say a field application, there would be some variation in the load demand, just the nature of the systems themselves, and of course the user in this case. And then looking at that modeling comparison, so as I mentioned, for the Anisi at full load, 5% plus minus, 10% plus minus at the lower, and then the Rover was in an alignment, I would say, with an agreement of those types of margins of error. So that was, again, a positive finding. So to summarize some of the key takeaways in future studies, so key takeaways, the Anisi overall closely aligns with the manufacturer's rated conditions. The system did experience clogging at that filter dryer, so right before the expansion valve, due to some of the refrigerant, and then a replacement ultimately did resolve that issue. There were large draws and longer cycle times, so that's going to ultimately be an optimal steady state condition for the Anisi unit. And of course, the Anisi unit should just be configured according to the application. You're going to want to configure it according to the application, run the appropriate flow rate, the appropriate return temperature conditions, et cetera, to make sure that you're overall optimizing the efficiency, the performance of the unit. And then the normalized data did suggest the experimental data is sufficient for modeling integration, where it hovers between 5 to 10%. And so for future studies, this is currently ongoing. So we're looking at hydrogen blend testing and performance curve development for this NEC GHP unit. We want to look at additional market-ready GHP experimental and field testing, ultimately for Energy Plus modeling integration and or GHP installation tool development. And then overall looking at system enhancements, so either varying heat exchanger configurations, including more temperature sensors, the inclusion of a tankless water heater. The list is kind of endless in that regard in terms of system enhancements that could be pursued for this. So I'll pause there. There's more, if you are interested in more information, please feel free to reach out to this email. Again, the study is publicly available, the comprehensive study that goes over this, but happy to take any questions now.
I see for Steve. I'll take you off mute. You should be able to use your mic.
Great, thank you very much. This is Steve Kowalski. I'm from the Oak Ridge National Laboratory, and this was a very good presentation. Thank you very much.
Sure.
I was curious, and maybe I didn't really quite understand. For the Anisi unit, I think in the beginning that you were mentioning that, well, it was described as an 80K unit, but it looked like the input rates, or I think it was describing the input rates, were somewhat less than 80K in the first couple of slides. Was I reading that incorrectly?
Let's see.
Yeah, see where we were. Yeah, a little bit back. Yeah, firing rate, was that right there?
Yes.
Yeah, so the firing rate, it looks like it's at 60 and it kind of goes down from there. So that's at 94% firing rate. I guess I was thinking that it'll be closer to 80. So 80 times 94 would be 16. So yeah, I guess it's just a little bit short. So yeah, I guess that's okay then.
Yeah, good
Right.
observation. Yeah, I think that when essentially how the unit is termed or coined, what they came up with that name, looking at the maximum under the most optimal conditions, and there might be certain losses or fluctuations that we might not be accounting for in this testing. But yeah, definitely good observation.
Okay. Thank you,
One,
Madeline.
one additional sort of follow-up on that question is, as I recall on each of those at the baseline, they actually commissioned the unit. And I don't know, I didn't see that. I don't recall, Madeline, but they sort of compared against the manufacturer's stated specs, and I think it pretty well lined up. But I do think they sort of forced the system to run at different firing rates just to perform the test matrix that were asked for.
Very good. That makes sense, Stephen. Thank you. Thanks, Madeline.
Sure. I think I see another hand. Let me see if
Yeah,
I can.
Scott Young had a question.
Oh, I can yeah, okay. I think I allowed you. You should be able to unmute yourself, Scott. Yeah, I'm not sure if they're, oh,
I can try it on my end, but it says
I
it's
can,
good, so I'll do it one more time.
yeah.
Okay. I think it should work now, maybe. Hmm.
His seems to be the one that we can't do that on.
It's because I allowed it, so the only option now is disable, so um hmm.
He said he could type. Maybe Scott,
Okay.
you can type your
Yeah.
question.
All right.
Any idea what causes the variation in capacity and COP at similar conditions but different tests? Sorry, I'm trying to, so you're saying, are you referring to the part load, different tests in that regard? Or you're talking about the steady state testing? Because if it's the steady state testing, it's just attributed to the difference in the firing rate.
Which they purposely adjusted for.
Yeah.
Scott, did that address your question, or is that not what you were asking?
Oh, I see. Okay, just looking at the spread at the top curve between 40 and 60 degrees Fahrenheit. So the top curve right here. Yes, okay. Yeah, because if we're looking at the difference when what's happening here, this is ultimately to be expected. Just again, variation of this x-axis normalizing factor. So the return minus outdoor air temperature. Yeah, let us know if you need any further clarification on that.
Did anyone else have a question? Or Scott, yours was addressed, correct? Oh, Michael has a question. I don't know if we can try to unmute him. He wrote it out as well. Michael's question is, what range of COPs would these GHAP units be typically displacing to give some more realistic idea of savings potential?
Yeah, so the typical operating conditions of that we're, I guess, gearing towards or thinking that these would operate at is between a 40 to 80 degree delta of the return in outdoor air. I think we're aiming for in this case, a high COP of about 1.2, given that this is what they're operating at. I don't know, Stephen, do you have additional insight into some of the field testing that's going on or some of those actual COPs that they're getting?
Yeah, I would say field testing is finding lots of challenges with realistic COPs, not because of the unit performance, but because of system integration. And there have been, Anisi's had some additional issues. We've not seen those as much, but just in general, the GHAP units need to be running flat out all the time, ideally would run when they cycle. They don't tend to work as well. I don't know if we've got a graph of that here, but in essence, they need to run a good 45 minutes until you're really at steady state COP. So if they cycle a lot, you're going to get poor field performance. If you keep them on, base loaded type of thing, you should be getting something pretty good. It's in the field. Part of the challenge is you're not only dealing with the unit itself, but you're dealing with the balance of the system. And so in the balance of the system, you may have a boiler that's cycling on and off because it's oversized, which we found to be the norm. And that brings down the overall efficiency. But if they pair it with a condensing boiler or a condensing instantaneous water heater, what you're finding is that the incremental of the GHAP isn't as much as you might otherwise expect, just because that one's topping it off at, say, 95%, AFUE or the equivalent. So I'm going to say you're probably up to about 30% on the better cases and, maybe 10% on lesser cases. There's a lot of work going on right now to try to address that because the units are clearly able to do better than that. So that's a long-winded answer to say what you test in the lab, what you get in the field are two different things, and that's not unique to these units. Did that help?
I think I saw a thumbs up from him.
Okay, did anyone else have questions? Good questions, by the way. Keep them coming. And I don't know who all's on the call, but just maybe serve as an FYI. This particular unit, the company's struggling right now. Sort of a unique design, but we started on the testing well before they were having some issues, and so right now we're not sure what their future is. But of course, we had pretty much wrapped up the testing before those issues came up. And Steve, you had a question?
I do. Can you hear me okay?
Yes.
Yes, okay. Sorry, Steve Kowalski from Oak Ridge National Laboratory again. I was curious, I think, Madeline, that you mentioned that there was a expansion valve that was a problem, or that there was a blockage near expansion valve, but this is an absorption system. I didn't think that it would have an expansion valve. Am I missing something on it?
Yeah, it's an absorption unit, but it also does operate like a heat pump. So there
Oh,
was it was in the filter right before the expansion valve. I think I misspoke, but yeah, nonetheless, there is still an
okay.
expansion valve in the
Got it.
system. Yeah,
Okay, thank you.
sure.
I think that expansion valve, and I don't know the details of it, is actually what gives this unit the ability to modulate. It's modulating flow, which of course controls the output.
Okay, thank you.
And Scott asked, do you expect to see the 40K unit from Anisi for a test? Given the status of Anisi right now, I wasn't aware they had a 40K unit, but right now the company's sort of in limbo, so I don't expect to see anything in the near term future. It looks like that answered his question.
Scott, you can come off mute. I think you have the option.
He's the one we're having problems with.
Oh.
What other brands do you expect to test? I know, Madeline, you want to fill them in on the tool testing?
Sure. Yeah. So right now we're working with GTI as well as several other stakeholders to kind of come up with a GHP integration tool that kind of outlines optimal conditions to install a GHP unit. So some of those partners for that, or some of those manufacturers that we're looking at for that overall tool, Rober, NEC, I think Vicont, correct? That hasn't changed, right,
Yeah,
Stephen?
the Vicot, which is how it's branded in Canada, or Homey, I think. I think it may be co-branded. I'm not quite sure I understand, but it's the same unit. It hasn't been in the U.S. market, but we think there's going to be some testing that comes out of that activity.
So yeah, or go ahead.
We're supporting the tool development as part of another project, which will have data from those two pieces of equipment. Are there any other brands that are expected to come to market? To our knowledge, those are the only ones in this space. The two Vicots, there's Rober actually has 2 units. They've got a lot more in Europe. They've actually been around a while. They're not all heat pumps. They've got dedicated chillers and lots of different configurations. And the Anisi one, which I mentioned, there is a industrial heat pump. It's more of a custom made one, just like chiller would be made. That one we probably wouldn't be testing in this type of scenario because it'd probably scale up too large for lab testing. But right now there's been a lack of some customers, so we haven't been able to do any testing on that one. Good information, Paul. Nice to hear there's an SMTI path forward. Yeah, that name, Arkla Cervell, sounds really familiar from the solar industry, Steve mentioned. And I don't know, I used to be more involved in solar, but there were actually 2 different brands of chillers, which in a way is very similar to the heat pump. One was lithium bromide, and I can't remember that. Yamasky or Yammer or something, and then there was ammonia water, which is sort of the same technology used here. Just FYI on related products. Any other questions? Give it a couple more minutes. All right, I'm not seeing any new questions. Madeline, thank you for your presentation, and I appreciate all of you that you attended. Oh, Paul just has another comment about the National Gas Heat Pump Collaborative meeting with Rober in Chicago. So on their strategic plan. Thank you.
Thanks all.
Thank you all, and have a great day. Bye.